has structure holes, Romberg structure holes, closure, openness, sort of things. And I want to sort of talk about one measure of structure holes. Well, first, some simple measures for openness and closure, and then there's the really constraint index from Romberg. Okay. So, okay, first I have to be able to move. I'm also going to put the chat really in the corner here. Why is this doing this? Okay. So as you probably remember, this is about individual level measures. And so one simple way of trying to capture sort of openness versus closure is to calculate gigabit density. So remember, we calculated density as the number of ties that were in a network divided by the potential number of ties a long time ago. But we can also do this for ego networks. So we can just calculate, we can just take a person, we take their ego network, so all the people that they're connected with. And then based on that, basically, we can calculate the density among these alters. Yeah. So here is the Florentine family network. I always have to be careful about doing this in Italy because my Italian is not good. I'll probably make wrong names for this. So I'm sorry for that. So basically the Medici here in the middle, if you think about their ego network, they have 1, 2, 3, 4, 5, 6 people that they're connected with, right? Now, if I look at this group as a network, and I remove Medici, because the Medici will always be connected with all the others, so I'm removing this, I can basically calculate the density among these alters. And that's giving a very simple measure of how much there's a closure versus openness in a person's ego network. So the Medici have 6 alters. The number of ties between these alters is 1. If I count it once, I can also count it 2 ways. As you know, as long as you're consistent, it's fine, the numerator and the denominator. So just checking. Basically, I have 1 tie. There could be 6 times 5 divided by 2 ties. That's 15. So I basically have a density of 1 over 15 or 0.06. Yeah. Is that okay? Very simple measure. In fact, any of the cohesion measures that we saw, we can actually apply to an ego network of a person. So we could look at how many components there are among the alters or things like that. So if I use the second one, the Peruzzi, then basically I have 3 alters for the Peruzzi. So anyone wants to calculate this? How many ties are there among the alters of the Peruzzi? 2. How many could there be? 3, yeah. Yeah, because it's 3 times 2 divided by 2, so that's 3. So that's 2 over 3, which is 0.677, right? 667. Okay, what about the Strozzi? Four altars, yes. How many ties are there? 2. How many could there be? 12 divided by 2, so 6, yes. So it's 2 out of 6, which gives me 0.3, yeah, 1/3. Yeah. Okay. So this is a very simple way of calculating an ego network and things like that. I can also calculate ego betweenness. Remember betweenness? Well, I can just focus on an ego network and calculate betweenness of a person. Just focusing on ego networks. So what I do is, and now again, I could have done it the other way. I just calculate how many times is a person in between others. So is the Peruzzi in between these two? No. These two? So I actually did it in 2 directions. We could have just done it once. These two? Peruzzi is on the shortest path between these two. There's no direct line between. So the Peruzzi are on the shortest path between these two because no direct connection there. But there is an alternative connection here as well. What do we do with betweenness? If there are multiple shortest paths, we divide by the number of alternative shortest paths. So in this case, there are 2 different ones. So it's only half a point. Okay. I calculated in 2 directions, so also half a point in the other direction. Shortest path, is Peruzzi on the shortest path? No. Also not in the other direction, so that gives me, in this case, 1 or 0.5. Just a question about making sure that the maximum betweenness would be, in this case, if there would be no ties between the altars, right? Okay. We can calculate it for this person, Strozzi. What do we get? So if the Strozzi in between here, yes. In between here, yes. In between here, yes, but half. So I did this one, I did this one. In between these ones, yeah. So 1, 2, 3, 3.5. Or if I double count it, I get 7. What am I missing? Not. I think I might be 7. Let's see if I have the answer. 7, yes. 3.5 over 7. And we can, of course, normalize it by taking the maximum and getting the values there. Yeah. So these are 2 simple things we could do if we have an ego network that we focus on. We could also do this for real ego networks. So for example, if I would ask you, who are your friends? And then ask you, are your friends with each other? I can also calculate the density, ego network density and ego betweenness, and still get measures for that to see to what extent you are like a person that's very, very close, that you always are hanging out with friends of friends, that all the friends of your friends, all your friends are friends with each other, or whether you're more an open person. There have been studies that have tried to link this with personality, specifically self-monitoring. Self-monitoring is a personality trait that sort of looks at to what extent you are adjusting yourself depending on who you talk with. So, for example, if I talk with one person here, I might be different than if I talk with another person. So some people have this tendency to really adjust their behavior depending on who they talk with. Others, and then there are high self monitors. There are two aspects actually to this, but let's make it simple. Basically, what it's arguing is that you monitor what you do depending on who you talk with. Low self monitors are people that do not care or will not adjust depending on who they talk to. They're like, this is me, this is how I am, and you get the same person with you or talk with someone else. So this has been one of the studies that's been with personality traits. There's others with respect to, for example, openness to new experiences. The idea that, sorry, I didn't tell you this, but then self-monitors, high self-monitors tend to really have open structures. So they tend to really build different networks with different people, and they don't link them with each other necessarily. There are big things about openness to new experiences. If you think about it, if you're more neurotic or closed, you don't want to do new experiences, what you might do is you will hang out with your friends, and through them you will build more friendships. Also maybe more introverts. Extroverts and people with higher openness for experiences might have a tendency to really, they see someone on the street, they talk with them, a random person, or they are in a pub, they just talk with a random person. Yeah? So you build, of course, then more open structures as a result. So these are some of the things that have been done and have been studied, where we try to explain why do some people have one behavior and others have different behavior. So who thinks they're more like a structural whole person and who thinks they're more like a closed person? So who would think that they're more like someone that would build their ties with each other, with the friends that are connected with each other? And who would see themselves more as like, I have very different friends and they don't know each other? Who says that they're more like, they like closed groups? Who thinks that they're in between? Okay, who thinks they're more open, like, they build like different networks to different people? Nobody? You're more, you have different groups, people. I mean, you can still have close groups, right? But it's more that you have a lot of different ones. Yeah. I think people that are student representatives, for example, that go towards like, these type of things at university, they tend to really have this sort of open structures approach. Okay. So, having talked about this, I now want to introduce you to Romberg's measure of structural wholes. Remember I told you that the centrality is difficult. Well, this one is, it's not difficult, it's just counterintuitive. It's just opposite of what you constantly would want to think. So I'm always struggling to explain this. It's sort of a simple measure, but it's also not. So the constraint index is the opposite of structural wholes. So your constraint means that you're being limited by your network. Yeah, it's sort of like, if you think about similar, it's sort of like your friends can dominate, but it's not completely the same thing. So if you have low constraint, that means you're very free to do whatever you want. Yeah, like the person that has 4 connections, none of these connections are connected with each other. You can free write, you can do all what you want. So this is a formula, and I want to talk, to go over this in detail. The paper I'm referring to is sort of the paper in the American Journal of Sociology, Structural Wholes and Good Ideas. This picture that you see has been used by, it's been found in a number of papers from him. So here's the answer. And then we'll go over the details. Yeah. And once we've done this, I think we should start doing some R again, because I've been postponing this a bit, but we should do this. But tomorrow we'll do some R. Okay. This is a formula, and we'll go over each of these examples one after the other. Yeah. What I want to do at the moment is just look at the result. So let's just look at what the number is that you get. And let's try to make sense of this. So A is the ego. And A, in this situation, is connected with two people who are connected with each other. In this situation, it's two people who are not connected with each other. This person is connected with four people who are not connected with each other. This person is connected with four people who are all connected with each other. So remember, a lower value means less constraint and so more structural holes. So who is of the four A's here? Who is the one that's the most structural holes? Or the least constraint? That one there, right? So what it's actually doing is it's saying, well, if you have a lot of connections, that makes each of these connections less burdensome, less dangerous for you, because you're relying on one person. And if they're not connected with each other, that's extra. So this is the best situation you can be in from these four situations. This is also good, but notice this is only a value of 0.25, sorry. This is 0.5. So here you're less constrained. And the lowest, I think the lowest you can get is 0. So that's when basically you're connected with a lot of people who are not connected with each other. And then you get higher and higher as you're more constrained. So for example, this person is connected with 4 people who are connected with each other. It's giving us a sum of 1. The total value, this value here is 1. What it's telling me? It's telling me that, okay, this person has quite a few connections, that's good, but they know each other. So that reduces the sort of impact of each other. If you have less connections and they know each other, that's even worse. Because now you just have 2 friends of 2 people you rely on, and they're connected with each other. So you get a higher constraint. Yeah. So we go from lowest constraint to highest constraint. And so it's a combination of closure that makes a constraint higher. So if you compare these with these, the left one is always higher than the right one. And the top one, because they have more connections than the lower one, always is going to be lower than the bottom one. Is that okay? Okay.
Clarify why in the bottom left case it's higher than the bottom right case.
So this is higher than this, because here you're more constrained. You have 2 friends, but they know each other. So that's more, you're less structural holes than here. Yeah? So remember, constraint is the opposite of structural holes. So you just have 2 friends and they know each other. Here you have 2 friends, but they don't know each other. So at least you have access to 2 different people and they can't control you. Here you have access to 2 people and they can control you. Yeah, so that's worse, that's more constrained. Think about sort of like claustrophobic feeling of having friends that know each other. You can't gossip with one of them too about the other. So if you have 10 friends and they all don't know each other, you can gossip with everyone about everyone else. Okay. If we get the idea, I will go over the formula. But I first wanted to make sure that we know where we want to go. And now we're going to talk about the way we go there. I, by the way, have the constraint index by iGraph, and guess what? iGraph gives a slightly different answer than the classic measure by Robert, and different than UCINet. But I'll come back to this. This is UCINet's answer. This is iGraph's answer. I'll come back to what's different there. So let's look at a real example. So the Barbadori are connected with 2 people. And now, even though the constraint index can be used for directed networks, we have an undirected network, which makes it easier. We don't have to think about, is it an outgoing time, ingoing time? It's the same. Okay. So what do we have to do? The first thing we have to do is to say, okay, this formula here has I, J, and then there's a K. I is the focal person, is ego. Yeah. J is the other person we're focusing on. And so we will do this twice. We will use J here, and we will use J here. And then if we use J here, then K are the other people that I is connected to. Okay? So we're going to look at all the pairs that every starting point is I, all the connections to other people. So this will be the J's. And we're going to go over J being from 1 to N, where N is the number of alters that I is connected with. Okay, so let's make this concrete. So the Barbadori, that's A. The Medici will call B, and the Castellani will call C. Yeah. I'm not using I, J, and K because I, J, and K are the generic names we give them, so we'll give them specific names, A, B, C. Okay, if I focus on A to B, so that basically means PAB. Well, what is this? That's the proportion of time or energy that A spends on B. So instead of using the connection or not, what Rombert is doing, it's saying, let's take A's connections and let's take the proportion of time that A spends on one person and on another person and another person. So this could actually work for valued networks. For example, I might spend 5 hours with you and 3 hours with another person, and 1 hour with another person and 1 hour with another person. That would mean that I spent 50% of my time with you, 30% with the second person, 10% and 10%. Yeah. So I can use this for valued networks. So the PAB is basically a proportion of time that A spends on B. There are 2 connections, both of them are 1, so it's actually 1/2. Yeah. So half of the time A spends on B. Is that okay? If not, tell me, right? Also online, if I'm trying to keep an eye on the chat. So, and then we're going to say, well, and now let's look at all the other people, all the Ks. So that's, if we focus on A to B, there's only one other person, which is basically C, right? And let's look at what proportion of energy or time A spends on this person. Well, A spends 50% of time on B, but also 50% of time on C. because the total sum has to be 1. And then we look at what proportion of time C spends on B. Is that okay? So it's basically saying, okay, for C, what proportion of time does C spend on B? Oh, C is not connected with B, so there is no proportion, it's 0. And if there would be others than C, the E and E and so on, that would be adding to this after. Yeah? And why is this important? Well, if this is 0, it means there's no overlap. Basically, the information, or let's think about it the other way. The fact that A spends time on B is unique in a sense it cannot get that from C, because C does not have a connection with B. If C would have a connection with B, that would be redundant. There would be no need to connect with B because you already connected with C and C is connected with B. Remember, you want to be connected with people that have unique information or that are not, connected with you other people. So if you think about it as unique information, if A is connected with B, A is connected with C. If C would get information from B, then you would be able to get information that's stored in B already through C. Because you talk with C and C would say, well, B said this. So there would be a connection here from C to B. That would make A's need to connect to B itself redundant. It would not be necessary, right? So the moment this becomes higher than 0, this term becomes higher than 0, and that increases. Oh, I see there is a mistake. There should be only 1, 0. And then this would become higher than 0, which would increase this value. Yeah, is that okay? So basically, constraint index involves 2 parts. This part, which is a proportion of time that A spends on B, and this part, which could contain more than just C, could be D, E, and F, and so on, which contains the indirect ways in which you can get access to B's information. So what is it doing? It's saying, how dependent are you on B? If B is a very important person for you, spend a lot of time with B, that makes you really depend on that person. That makes you constrained. That's this part. And if there's other ways of getting information about B through other people, that's like this. That makes you more constrained. That makes it more redundant. That makes it less necessary to have connections. So that's basically what this formula is doing. It's the proportion of energy or time that you spend on J and the proportion of other ways in which you can get information about J. And then you go over this for all the J's, so all the connections that you have. In this case, because we assume that both parts, the question is, how do we know that B and C would? I'm going to go there because there's also a quick moment. So the question is, how do we know whether B and A spends as much time on B and C? The only way we know is by having a network relation that captures the strength of the time, or the time spent with a person, or things like that, or how influential that person is to you. In this case, it's just binary, so it's 50-50. But otherwise, I would collect data about, how influential do you think, Badori, how influential do you think Medici are to you? How influential are the Castellani? They say 7 and 3, 70%, 30%. Okay. So there's no tie here, so I'm going to use a comma. But yeah, there is something here. There shouldn't be at second 0 because there's just one other term. So now I can do the same for the Castellani. So the Castellani, 50% of the Barbadores time is spent on C. That's a constraint I have to take into account. But then there's no indirect way of getting information about C from others. So that's 0, even though the Barbadores spend 50% of time with Medici. Is that okay? So we get this part, right? Now what we do is we take the second power. I didn't talk about this yet, but it's the second power that we take. There's a reason for that. We'll see that. Take the second power. So this gives me 0.25. 0.25. I take the sum of that. That gives me 0.5. Yeah. Let's see if that was what we got before. Yeah, that's 0.5. Yeah, that's this thing. Okay. So what happens if I only would have one connection, like the Pazzi? So Pazzi is 100% dependent on the Salviati. So that is 1/1. But then, of course, there are no indirect connections because there's only the one connection. So that's just 1. So your constraint index, if you're connected with only one person, is actually 1. What if I have 3 connections, like the Albizzi? So the Albizzi have 3 connections, and there are no connections between alters. So 3 connections means 1/3 of my energy I spent on Medici, 1/3 of my time or energy spent on the Minori, and 1/3 I spent on the Guzaini. It's good that I have a mask. You can't hear that I'm mispronouncing the names. Yeah. Now there are no connections between the alters, so it's 1/3 times 0. The time, so if I look here, it's the time that this is the time that C spends on D. There's nothing there. Time here is the time that D spends on B. There's nothing there. So that gives me 0 and 0. So just is 0.323. Second power gives me 0.111. Same here, same here. I take the sum of that. Gives me 0.333. So actually what's happening is, if I'm connected with a certain number of people, because I take the second power, it's actually 1 over the number of people. That's my constraint index. As long as there are no connections between the alters, that's what happens. Because the only thing I do is I take the proportions, but instead of taking the sum of the proportion, I take the sum of the square of the second power of the proportion. Yeah. Good. Is that okay? So what happens now if I do introduce some constraint? So again, 1/3 of the time on this one, 1/3 of the time on this one, 1/3 of the time on this one, right? Now, the B here, there's no connections towards B. So any of the others, this part here is 0. Because that's always 0. That gives me 0.111, just as before. But here's where it becomes different. So now I have the Picheri, the Strozzi. So 1/3 of the time I spent on Strozzi, but there's no connection here, so that's 0 here. But this one, now I actually can get information about the Strozzi already through the Peruzzi, right? So this is a bit redundant. Because I can get information this way. So the connections to the Strozzi is 1/3, third of my energy, plus 1/3 on the Peruzzi, who themselves spent 1/3 of their time on the Strozzi. So notice this part now is larger than 0. And how large is it? Well, it is 1/3 if I take into account that D has 3 connections. So 1/3 of the time they spent on the Strozzi. Okay. And I can do the same for the Peruzzi, and guess what? It's just a little bit different. And why is it different? Why is this different than this? Looks the same. They have a common node, but C has 1 more connection. So only C spends only 1/4 of its energy on D, or time on D. So think about it this way. If you think about it, is it worth to go and get connection with D for A? So for A, is it worth to be connected with D? It's more worth to be connected with D than it is to be connected with C. And the reason for that is because C actually spent more time on other people. So, whereas D doesn't. So this is why this is different than this. And if I'm not mistaken, that should match with 0.4823. Yeah, is that okay? Now, the difference is that actually, so this is the iGraph approach, but actually, what the classic approach does is it's saying, well, we shouldn't take into account that there are other connections because we're only looking at the ego network of A. So any other people that D, C, or B are connected with, the blue ones, that are not connections with A, we should ignore. And so instead of saying that's 1/4 and that's 1/3, it says it's 1/2. There are only 2 connections. That's a small difference between the sort of classic BERT measure and the measure that iGraph uses. Is that okay? So, what happens if we go further? There's more connections. Well, this value increases slightly. And let's see if I have another one, or is this everything? No, that's no. So when I have the gratings, it's the iGraph value. If I calculate the yellow things, it's actually the UCINET version, or the classic BERT version, which does not take into account the blue ties. Okay, are there any questions? Okay. Oh, sorry. iGraph is the part as package in R. So it's the SNA package and you have the iGraph package. SNA does not have a constraint index. So the package we used before does not have a constraint index. iGraph does. But iGraph uses a specific version here. So whereas basically instead of, so iGraph uses all the connections, including those that to people that are not connected with A. UCINET and classic BERT approach would say, no, we can't include this because they're not part of the ego network. So if we would have an ego network, we would not know about it. Yeah. Okay. So this is how we can do this. I'll do this another time. This is another exercise. Okay, I thought this was going to take longer. So should we do something more? How do you feel? Tired or not? How was your day? Let's do an exercise then. Yeah. So let's calculate the constraint index. Oops. I don't want to actually close this. I want to keep it, but not this way. Uh-oh. Well, let's do it this way. Shall we do a little exercise to check that you got this? So. Yes, I know. I will, for those online, I will share again in a minute. I'm just making my little network here. So this is A, B, C, D, E, F. I'll just do this. And then a few connections here. Not too many, because that's too much otherwise. Okay. And now I'm going to give these values. Okay, start again. And now I can share my screen again. Okay. So focus on A and try to see if you can get this to work. Probably should have copied this picture. The formula here. Okay, sorry, I'm going to come back. Sorry, people online. Okay. Have some fun. Yes, so 40 is just probably. So basically use low formation. Mm-hmm. So now. So the numbers are how strong connection is, and it's directed. So there is not that many, but there is a few. Sure, yeah. It's just so tempting if you're online to just like click on that. Okay. Can we start with these ones? So A to B, what's the thing here? So what proportion of time does A spend on B? 2. Sorry, 2 out of. So I'm using valued networks here. 2 out of 2 plus 5 plus 1 plus 1 plus 2. It's 4, 5, 10, 11. Right? That's why I use this, so there's like values. And then plus nothing, right? So plus 0, and that to the second power. That's that. So that would be the value for this connection. Yeah. Okay. What about C? So it's 2 out of, no, it's 5 out of 11, right? Plus a lot of zeros, but there's one way we can indirectly go to C. Right? That's going via from A to D and then from D to C. So I have to add this one. What proportion of time does A spend on D? 1 over 11. Right? And what proportion of time does D spend on C? 5 out of? 7. 5 out of 7. And I take the second power of that. And that's a constraint. So there's a constraint of actually spending a lot of time with C as A, quite a bit of time, plus the fact that I'm also spending time with other people that spend time with C. That increases the constraint. So it's not just that I spend a lot of time with C, but I'm actually I'm spending a ton of time with C who actually is indirectly I'm already indirectly connected with, whose information I already get a little bit through other people. How much of that information do I get? Sorry, do I get? Well, 1 out of 11 I spent on D, so that's not a lot. So think about it this way, the chance that I get information about C through D is going to be going to be low because I don't spend a lot of time as A on D. But D does spend a lot of time with C, so we'll get a lot of information from C. So that's like, that's why this is a product of these two. Yeah. That okay? And then I take the second power. One reason also why it's the second power is because it's a product of two proportions. So, but then it's the other part. Okay, so let's do D. What proportion of time does A spend on D? 1 over 11, that's not a lot, yeah. Plus 0, yes, because there are no incoming ties. And this is the counterintuitive part, because you always think about the outgoing ties, right? You think like, oh, there's outgoing ties, but no, it's the incoming ties that you look for. It's how much other people connect to this one, rather than how much this person gets information from others. It's how much other people, other connections of yours actually also get. Yeah. Okay. What about E? 1 over 11, yes, plus. Okay, 2 over 11, that's the F one. That's this one. Times. Yeah, 2 over 2 or 1. I'm just doing 2 over 2, so everyone it's clear that that's the second power, yeah. So F gets all its information from E. Oh, sorry, and then, of course, sorry, and then the other one, D. So 1 over 11 spent on D times, how much of does D spend on E? 2 out of 7, right? Yeah? Sorry, I forgot that was this. So there's two constraints here. I mean, two indirect constraints. One direct, but it's a small one, 1 out of 11. But then there's indirect ones. And actually, this one is going to count maybe a bit more because F is only having. Great. Because you're looking at D, and it's these outgoing ties, and D does not have a connection to A. Because I on purpose put it so that it's. If there would be a mutual connection, then it would be 8. Okay, F spends 2 out of 7, 2 out of 11, plus 0. I'm just putting 0 there so you remember that there's nothing to the second power. But okay. So what do we get as an answer? Anyone able to calculate this? I have no idea. I'm guessing it should be smaller than 1. Because there are quite a few connections and they're not connected with each other. But so that's roughly 1/10, 2/10. That's 0.04. That's a little bit higher, that's half plus. Let's say it's 0.25. 0.60? I don't know. Rough guess. You want to know that's very. Otherwise, we can do it for tomorrow. So the sum should be 0.458. Okay. Yeah. Could be something like that. Good. So let's just make sure. Okay. What is going on with this thing? Oh. That's fine. So let's just recap to be sure. I'll just answer that in a bit. Let's just make sure that we got this. So I'm sorry, this is there still. As we have more connections, our constraint index reduces because the first part, the Pij, is going to become lower and lower and lower, even if we sum it. The second part is impacted by the red part. So the lines to others is the Pij. The Pik times Pkj is the red lines, the connections among alters. That's driving that part. Yeah. And so there's always two parts to this constraint index. There's the degree related part, how many different connections you have, or in valued networks, how divided you are in your resources, in your time. The more divided, the better. So having 2 times 50% is better than 1 times 90% and 1 times 10%. Yeah. And then the other thing is the connections. Okay. That's basic constraint index. It's not that difficult, but it does take, you need to take time to think about when you do this. Yeah. Okay. I think that's it for me for today. If you want, you can stay here and we can chat about stuff. Yeah? If not, I will see you tomorrow. So tomorrow we'll use R. And we might use iGraph instead of SMA. Oh, by the way, if someone wants to talk about dissertations, if you want to do some network dissertations, you know, talk with me or with other people. Oh. So. Hi.
To ask you something about the visualization of networks.
Okay.
Well, I'm currently working on a big network.
Okay.
And I don't know.
Can you give me 1 second? I'm just going to answer for, I think, Gabriel, then Dance. November.
But first I tried to create with then I did some research, so I used
How big is it? Sorry?
500,000
Okay. But how many nodes?
150.
Okay.
But I had to find
Okay.
still, I use the data view to visualize just a subset of images, but with the just add two ends. And cannot import the images. So I was wondering how some tools that I can use to import all these edges and then visualize just
So you're importing it into R.
into still JavaScript.
And R would not be.
I don't think so because